Yes, okay, right. Okay, the true subcritical bifurcation, mathematically the definition, I accept only this one here. Okay. But again, physicists will often call this, with the whole thing, a subcritical bifurcation. But the different, okay, still, this looks like a supercritical bifurcation in that over here you had one stable point, and over here you have an unstable surrounded by two stable. So what's the difference between that and a supercritical bifurcation the way we defined it? Because this one has hysteresis, meaning it has, that's what you were driving at, yes. Meaning, here you have a point. If you are increasing mu, which mu is something that it's called a control parameter, meaning that the experimentalist or the numericist controls it. If you're going up, you'll get to here. Oops, now you're unstable, and you'll go to here. But now, if you're here, you go up, you keep going. But if you go down, you'll go here, and then you'll go down here. So you have two critical points at which you make transition. Whereas with a supercritical bifurcation, the ordinary way, you would only have one point, which would be here. You would here, and you would leave, and you'd come back, and you'd go there. Whereas in this stabilized subcritical bifurcation, you're going to know about it because it will be, you'll have this hysteresis. You'll never be able to get close to zero. You have this gap, and the transition from zero to the higher branch takes place at a different mu value than the transition down. And that's how you know about it. Yes?
Do you mind if I just ask questions about the cell node bifurcation, parabolic example before? There is, so with the cubic example there, where you had one single root, you had a stable node.
Yes.
I'm probably using the
No.
wording.
Node is the right word there.
The previous slide, I think?
Wait, this is the saddle node. This one?
With one single root here.
Oh, the marginal case.
Yes.
Yes. The marginal case, what do you do there? I think you just hang around forever. I'm not sure what you do when you're really just on that point.
Oh, okay.
It's a set of measure zero, I don't
Okay.
worry about it. But yes, you have algebraic growth maybe? What do you have there? Not exactly sure.
Okay.
Okay. I mean, you could have, in fact, I guess the same question if you were right there in the mu equals zero point there, or any exact bifurcation. Okay, other questions? Anything, comments? Okay, thank you for those questions.
And it's a pitchfork because?
Pitchfork, because this looks like a pitchfork, kind of, like a devil's pitchfork, you know, or pitchfork in farming, you have a round thing, you know, there, right? It's true, I had said I would say why it's a pitchfork, right? So, but take this and turn it, and so it's a pitchfork. Good, thank you. Okay, so technically speaking, these things are not pitchforks. There's no bifurcation. This is a saddle node bifurcation here. And this is just continuously going from here. And this thing here is actually many bifurcations. It's a subcritical pitchfork and then two saddle nodes here. So you notice there are saddle node bifurcations appearing all over the place. They are very, very common. They're the most common thing to happen. But you know this. The study of dynamic systems is very similar to the study of roots of polynomials. It's the study of roots of functions. All functions are polynomials, effectively. That's why we have Taylor series. And how do roots appear and disappear? Even a polynomial of order 29. What's happening? Well, what always happens, you know, you have your 29th order polynomial, you know, whatever it is. How is it going to change its number of roots? Well, at some point, it's going to do this. It's always going to be locally quadratic. There'll be a place where it did this, and then where it did that. And it may be a 29th order polynomial, but when you study the changing in roots, it's always going to be just as if you had a quadratic polynomial. That's why, and it's for that exact same reason that there are saddle node bifurcations all over the place. A bifurcation, I don't think I mentioned the name of that term, that is a change in the number or stability of solutions of a system. And that always happens, or almost always happens in this way. And there's a word for almost always in dynamic systems, and that word is generic.
Excuse me?
Yes.
how exactly is this hysteresis happening? Like, I didn't quite understand when you draw the path, what's coming back.
Well, you're stable here, so there's no reason to leave. You're increasing your mu. You just stay, 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 stay. But now you're not stable. You have arrows, we had drawn the arrows here, that bring you here. And now, when you're here, well, you're stable this way, you're stable that way. So here, okay, but over here, so you're going to go down, 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 and here you'll have the same mu value, but instead of being here, you'll be here. So it's history dependent. If you were coming up, you would have been here for this mu value of, say, -0.5. But if you're coming down, then at this value of -0.5, you're going to be up there. History dependent. I'm not sure, that's not where the word hysteresis comes from. No, one has a Y and one has an I. But still, we can think of it. It's a coincidence. Hysteresis means that it's...
It's something to do with hysteria, probably.
Yeah, but
Go
what?
there.
Okay, but let's pretend it means history dependent. So if you're going up, you'll be here, and if you're going down, and you're at this mu value, you'll be here. So you have one point where you jump from here to from the high value to the low value, and that's here at -1 for this particular case. And you have a point where you jump from the low value to the high value, and here it's at 0.
And in an experiment, would it be possible to get to that island region on the right-hand side?
Here,
Yeah.
get to here, no.
Okay.
No. Here, no, we'll just say no. Okay. Okay, so here's some mechanical examples. I'm mostly going to do fluids, but it's just the bifurcation theory was first invented in solid mechanics. Here's a simple mechanical example. Here you have a loop of wire, somewhat flexible wire, and neither totally rigid nor totally flexible, and it's going through a plank. There's 2 holes here. And so here it is sitting upright because it's got a certain amount of rigidity. But now if you make it longer and longer, eventually it's not that rigid, and so it will flop over one side or the other. Okay? So that is, so here's it seen from the side. So here, let's turn this here, and this is when it's standing straight up, and this is when it's flopping. So if you measure theta, you will eventually see it flop. But now, if it's flopped over, and now you start to shorten it, the value at which it will then eventually flip and be straight is lower than the value at which it flipped. And that's how this hysteresis was first discovered like that, or was first formulated. This is the value at which it flops over, and then this is the value at which it comes back to being rigid. And all these has to do with the rigidity of the wire and the length. You non-dimensionalize this length and the rigidity of the wire. And so that's an example of the subcritical bifurcation then stabilized with the other term, and then an example of an imperfect pitchfork bifurcation. Again, all this was discovered first in solid mechanics when they talked about the buckling of beams. So you have a beam and you have a weight and you push it down, and then eventually the beam is going to bend, right? And so perfect beam, it will bend with equal likelihood in both sides, but your beam is never perfect. Here's an exaggeration of an imperfect beam. You can see this very imperfect, so you can see it. As you bang down, you can imagine what it's going to do. It's going to do this. That's what it wants to do, this one. And so that's what it's doing. But the other branch exists. If you could somehow persuade it to go the other way, it would do the other thing. A perfect beam will do this. A slightly imperfect beam will do that. And now, one last kind of bifurcation, and that is the end of the list of steady-state bifurcations. This one's called transcritical, and it combines some features of the two. There's a quadratic term, and there's a linear term here. So you can, this is the, so, excuse me. So if you look at the steady states of this, you look for fixed points, and there are 2 of them. There's x equals 0, and there's there's x equals mu. So x equals mu, of course, looks like a straight line. X equals 0 looks like this. So you could say that this bifurcation doesn't really exist. There's just always 2 solutions, right? Remember, bifurcation is a change in the number or stability of solutions. But there is a change in stability, as you can see over here. And if we can look at the f prime of x bar, the derivative of this function is mu minus 2x. And for x equals 0, this is going to be mu, meaning that it is negative, excuse me, x equals 0, for mu negative, I'm sorry, why? No, that's right, it's mu for x bar equals 0. Do I have this wrong? Just a second. No, that's right. It's going to be negative for x for mu negative, meaning it's going to be stable. This x equals 0 solution is going to be stable here, and it's going to be unstable for mu positive here. And this other one, if you put in for x bar the other solution, mu, you get mu minus 2 mu, meaning minus mu, so it has the opposite stability. And you see that, this one's stable, this one's unstable. So sometimes this thing is called, in the olden days, in the 50s or 60s, this thing was called merely exchange of stabilities. Because these branches meet, they exchange their stabilities, and they just go on. Right? And this is what it looks like. They, here you have down, and here you have down, up, down. And often, again, what people, since this diagram has something in common with the subcritical pitchfork bifurcation we mentioned, meaning that some trajectories go off to infinity. And remember, physicists or other scientists don't like going off to infinity. Where is this infinity place of which you speak? So they put in a stabilizing term here. If you put in then a cubic term with the correct sign, you can stop those trajectories that go down to infinity and make them stop here. And that's with this and then a cubic term. So now we can summarize, okay, this is everything about all the steady bifurcations that exist in 1D. And it's pretty much all steady local bifurcations. Okay, and we can organize them all in what's called the unfolding of the pitchfork. So everything we've talked about has been small polynomials, and we've gone up to cubic order. So here's a general cubic polynomial, right? And you can see I've kind of prejudiced things a little bit because the pitchfork, remember, was mu x minus x cubed, and it doesn't have any names, whereas here I've called alpha and beta x squared, other terms allowing me to change the alpha and beta. So this picture summarizes everything that we've done so far. This is the alpha and beta plane. And at each point in the alpha and beta plane, we're going to put, there are 4 dimensions here. There's mu, x, alpha, and beta. At each point in the alpha beta plane, we're going to put a little x as a function of mu diagram. So there's going to be a bifurcation diagram for each value of alpha and beta. For alpha equals 0 and beta equals 0, then we have the regular old pitchfork. Right? You remember that? Like that. Now, because it would be too confusing, I'm not putting in the dashes. I'm not paying attention to stability anymore, just the number of fixed points. So you recall this picture. It's a pitchfork because it looks like a pitchfork, right? Here it is. You recall we said that when you had an imperfect pitchfork, you remember I talked about adding a constant, and that's adding an alpha. And I produced, I think before this picture, I could have added an alpha of the opposite sign, and we would have gotten this picture. This is the imperfect pitchfork on either of these two sides. And you remember that. That's alpha plus mu x minus x cubed. And what about the beta? You recall we did this too. We did the transcritical bifurcation, mu x plus beta x squared. But we didn't like that because it went off to infinity. So we added a stabilizing cubic term. So it wouldn't do that. And that's here and here. So here we had a transcritical bifurcation like this. You see the transcritical bifurcation here? This is in, I think, the previous picture. Yes, we had something like this, which has this equation with a cubic term, minus x cubed, here. And that's what produces this picture. But of course, we could have it be on the other side. Nothing says it has to be on this side. And these two pictures are found here and here. So this is what happens when you add some alpha, a constant. This is what happens when you add some beta. an x squared to the pitchfork. We've already seen these pictures. And if you add both of them, if you add both a constant term and a quadratic term, you get all these other pictures that we've seen here. This thing, once you add a constant, this is going to separate. You no longer have x equals 0 being a solution throughout. Once you put in an alpha, if alpha is 0, then x is, which happens here, then that straight line is always blue. It's always a solution. But once you put in a non-zero alpha, that's not true anymore. You don't have a vertical line that goes through. And here you have these imperfect bifurcations, which get so imperfect that they end up, this one can even become S-shaped like that when the beta gets big enough. So we could describe all of this is the pitchfork bifurcation, and when you unfold it, that's what it's called, when you add other terms of no higher order, but that were missing before, you add all the possible lower order terms, you get a bunch of saddle node bifurcations. Remember we said saddle node bifurcations are what really occurs all the time. That's what was over there. So what do you have here? Here you have 1, 2, 3 saddle node bifurcations. When you really break this pitchfork, you turn it into 3 saddle node bifurcations. Okay? But again, if you didn't have your glasses on and you saw this from way, 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 way back, they would all kind of look like pitchfork bifurcations. But if you measure well in your experiments, you might find some hysteresis. You would find things that tell you that it's not exactly a pitchfork bifurcation. And we'll get to the why it's called saddle end node in just a second, right?
But I have another question.
Oh, good.
So, right. So what's your explanation of what the meaning of normal form is?
Yes, yes. Okay, I'll say some words, but I'm not sure it's the right words. Okay, the normal form is the simplest functional form that will give you the behavior that you're looking for. Is that kind of good? Yeah. The simplest, yeah. Okay, so again, you recall over here, we said, but wait a minute, we won't always be in normal form coordinates. And here I said, well, no, we can move everything around and put ourselves into that same coordinates by rearranging them. But that's a lot of trouble to do that and to do all the algebra. So what would you do if your thing wasn't in that normal form, but you kind of knew it had this behavior? Well, you would check for all these derivatives, and if they were positive, if they were zero, if they were, you would find it. Instead of having to rearrange everything to move all your fixed points to be, all the bifurcations to be at 0 and all those things, you would just check all these conditions. Okay, now, let's see. Right. Okay, so we come to systems with 2 or more dimensions, because after all, most things are not one-dimensional. Many things just carry over. So let's look for x dot equals f of x, fixed points 0 equals f of x bar, but now each of these is an n vector. And let's do the same stability calculation as before. We perturb x bar by epsilon. Epsilon is a vector, x bar is a vector. But now our Taylor series, this is now a matrix. This is the Jacobian matrix that contains all of the partial derivatives, dfi, dxj, for I and j running from 1 to capital N. So here you have the Jacobian matrix acting on a vector. The next term is not so important right now because we're going to neglect it, but this is called the Hessian. It's got 3 indices. It's the matrix of second derivatives, okay? But this is the only one that will concern us. Since we have a fixed point, this is true for all of the n equations, so this is going to be 0. And so we'll have, the equation we'll be left with for the evolution of the vector epsilon is epsilon dot equals Jacobian times epsilon. And the solution to that is the same as if this were a scalar, meaning it's the exponential of this matrix times t on the vector epsilon of 0. Now, what does this mean? Let's look at a matrix that has real eigenvalues. And the way I like to do is, let's do with Taylor series. Taylor series will tell you everything about functions. So the Taylor series of e to the at, this is a matrix. and this is going to be a matrix. And how do we know that we could write e to the at at all? What does that mean, exponential of a matrix? Well, the reason exponential is an analytic function, meaning you can represent it as a Taylor series. Taylor series use only multiplication, scalar multiples, and addition, and multiple of matrices. And we know how to do that with matrices. So how do you define, or to me, a non-mathematician, how do I define the exponential of a matrix? I define it by its Taylor series. And this, of course, has meaning. You can, A, of course, you know. A squared, you know, too. It's the product of two matrices. A cubed, you know, gives the product of A times A times A. And you know matrix multiplication. So you can do this. I mean, you can define it that way. How would you actually carry it out? Well, let us diagonalize A, and let us write it as, I must have written this someplace. Let us write A, here it is, as V lambda V inverse. That's what it means to diagonalize, where lambda is a diagonal matrix containing the eigenvalues. V is a matrix that contains the eigenvectors one after another, and V inverse is the inverse of that method. Or it also contains, if you want, the left eigenvectors. That's the inverse of it. So we can just substitute for A, every place that we have an A, we can write V lambda V inverse. And for I have, for the purposes here, substituted V inverse. And we can do that all the way through. So notice once we have A squared, we have V lambda V inverse, V lambda V inverse. Well, we can collapse the V inverse V. And that's the same for the cubic, too. We could collapse all of them. And what we end up with is a V on the left, always, a V inverse on the right, and in the middle we have the identity plus T times a diagonal matrix plus T squared over 2 times the square of that diagonal matrix, and so on. And the square of a diagonal matrix is merely the square of the individual elements. It's very easy to square a diagonal matrix. So that's what's shown here. That's just squaring the individual elements. And hence, what you end up with is a matrix. Excuse me, when you take the let me go back a couple steps. To this, we can put this back together again, just as we took it apart. We can put back together again this Taylor series to write e to the t lambda here. But we know what that means. We don't have to do matrix multiplications over and over up to the 8 to the 15th or something. We know what that is. That's just the exponential of those eigenvalues, the lambda. And you can see how this would be easily extended to, this works for matrices of any size. I did it for 2 by 2, but it could be any size. And what I have to do, of course, is this is basically going to eigenspace, going to the space representation in which the matrix is diagonal. Then I do this exponentiation of the eigenvalues, and now I go back from the eigenspace to the regular space. So it is easy to take the exponential of a matrix, so far with real eigenvalues. Okay, and what we get is the same kind of thing that we got before, an exponential of a scalar times t. And this thing here is going to cause growth if lambda 1 is positive, and it's going to decay if lambda 1 is negative, and same for lambda 2.